All right, so 5.3, we're talking about independence and the multiplication rule. So first, let's define independence. When we talk about independent events, we're talking about two events that don't impact each other. So me riding my bike and me doing well in school, those are independent events. Me flipping a coin and me rolling a dice, those are independent events. The outcome of one does not affect the outcome of the other. Doing homework and getting a good grade on a test, those are dependent events. Doing more homework is going to impact, hopefully positively, your test grade. So those are the two different types of things. We're talking about independence means the two events don't impact each other. And then we're going to be talking about the multiplication rule. So starting off, suppose you roll a dice 2 times in a row. You get the first time you get a 3. On the next roll, what is the probability that you'll get a 4? So if we got on the 3 on the first roll, what's the probability that you get a 4 on the second? Well, the probability of 4 is 1/6. Those two events are independent. The first roll doesn't impact the second roll. So they are independent of each other. You're playing a card game with 3 of your friends. You draw one card out, you look at it, then you put it back in. Then your friend picks a card from the deck. Are those two draws independent? Yes, they are independent, and the reason they're independent is because you put the card back into the deck. If you don't put the card back into the deck, then it's no longer independent because you are affecting the card that your friend can draw. So as long as you put it back into the deck, it's totally independent. Next, we're going to talk about the multiplication rule. We use multiplication when we talk about and. Or is addition, and is multiplication. Is multiplication. So if we're talking about independent events, two events that don't impact each other, the probability of the and, them both happening, is the probability of A times the probability of B. So a coin is flipped and a die is rolled. Find the probability of getting a heads and a 4. So coin is flipped, die is rolled. Those are independent events. And so we're finding the probability of A and B. Coin is flipped and we're looking for a head, so that probability is 1/2. Times the probability of getting a 4, which is 1/6, which is equal to 1/12. Now, another way of looking at this and of calculating this probability is by setting up a tree diagram. So if we set up our tree diagram as heads and tails for our first event, which was flipping a coin, and then we look at our second event, there we go. So we have our tree diagram. Heads, tails, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Now, how many of those events are both heads and a 4? Well, just one of them. It's this one, which is heads and 4. Well, how many total events are there? There's 12. And that's another way of getting to that 1/12 answer. All right. Next problem. A card is drawn from a deck and replaced, and then a second card is drawn. Find the probability of getting a queen, then a diamond. So, queen is A, diamond is B. Since I'm putting the cards back, since it is replaced, they are still independent events. So, the probability of A and B is equal to probability of A times the probability of B. So now we have the probability of getting a queen is 1/13. The probability of getting a diamond is 1/4. And so the probability of getting a queen and then a diamond is 1/52. All right, take a second, read this question, try answering them, and then unpause and come back and see if you got the same answers I did. All right, so a couple things in here to pay attention to before we get started. First is that we talk about being replaced, and so that's going to make them independent events. If I picked a marble and then I kept that marble out, these would not be independent events, and so I would have to use a different formula. So next, I look at the total number of marbles. There's a total of 10. And then we go through and we find all of those probabilities. Probability for A is the probability of getting a blue and then another blue. So probability of B times probability of B, I get 1/25. A blue, then a white. And again, I'm using that upside down U looking shape instead of and. They mean the same thing. And then for D, a red and a blue and a white, you just multiply all three of them together. And you can extend that multiplication property as far as you want. So you can have 3 events or 10 events or 100 events that you are multiplying them all together. Next, the probability that a randomly selected 24-year-old male will survive the year is 0.9986. So if you ever get into actuarial sciences, they do stuff like insurance adjusting and stuff, and come up with risk tolerances. There are giant books and tables that have these kind of numbers and stats in them, which talk about how likely you are to survive the year or to die or to get your car stolen or whatever, based on how old you are, where you live, how expensive the car is. All of these types of things have a probability associated with them. So if you have car insurance and you are young, your insurance costs more because the probability that a young person gets into an accident is higher. Or if I used to live in Inglewood, and so Inglewood had a area code or a zip code. When I moved from Inglewood into Littleton, my zip code changed and my insurance changed as well, because the likelihood of having my car broken into based on your zip code changes. And so your insurance will go up or down based on the probability of something happening and them having to reimburse you. So that's where this number comes from. It is a real number. It's not made up. There are giant books that have all sorts of probabilities in them. So back to the question, what is the probability that 3 randomly selected 24-year-old males will survive the year? Well, what we're looking for is the probability of survive, and another person surviving, and another person surviving. So what that really is probability of survive times the probability of survive times the probability of survive, which in math we simplify to the probability of surviving cubed. So the more of the same thing we have, we just keep raising it to a certain power. So in this case, we're looking at 0.9986 cubed, and that gives us 0.9958. So the probability of picking 3 randomly picking 3 24-year-old males and having them all survive the year is still very, very high. Now what if we do 20 of them? So again, it's the same principle. We're still taking that probability of surviving. This time, we're raising it to the 20th power. And this time, we still get a fairly large number. Still 97%, over 97%. All right. Next, we're going to talk about at least one probabilities. And this is going to be the last thing we cover in 5.3. At least one means one and all of the other numbers. So at least one means greater than or equal to 1. So when we're talking about things that could happen, we can't have negative things happen. So at least one covers all of the possibilities except one possibility. So if I say at least one car accident, how many of you have had at least one car accident? Well, you either raised your hand or you didn't. If you didn't raise your hand, why didn't you raise your hand? How many car accidents have you been in? If you didn't raise your hand, it means you've been in 0 car accidents. So we're going to use the fact that at least one means everything. At least one is everything except 0. And so we're going to use our complement rule, which divides up all of our probabilities along with this at least one probability to make your life easier. And so this is the formula we use when we're talking about at least one. So what's the probability of being in at least one car accident? Well, it's 1 minus the probability of not being in a car accident, because there's only 2 sides to be in if I talk about at least one. You could either have 0 or you could have at least 1. So let's give a quick example. You toss a coin 5 times. What is the probability that at least one of them is tails? Well, the reason we don't go at this the regular way is because if I start listing out all of the different ways I could get 5 coin tosses, so that would be 2 to the 5th. That means there's a sample space of 32. And if I want to get at least one tail, that means I could have one tail all the way up to 5 tails. And that one tail doesn't say where that tail is. So I could have heads, tails, heads, 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 or I could have tails. And so it's really complicated to figure out all of the different ways that I could get at least one tails. There is, however, a much easier way to approach this, and that is, well, at least one tails is our event. What's the complement of that? If A is at least one tail, then the complement of A is no tails, or in this case, 5 heads. Now I can find the probability of 5 heads, because that probability is heads and another heads and another heads, another heads and another heads. It's the same thing we just did. We need to find the probability of heads, which is 1/2, and then we raise it to the 5th power, which means the probability of all 5 being heads is 1/32. And that wasn't super difficult. Now I need to turn that around to look at least one tails, which means A is equal to 1 minus, the probability of A is equal to 1 minus the probability of the complement of A. So what's 1 minus 1/32? Well, the probability of A is 31 30-seconds. And that's how we can use our at least one probabilities. A game is played by drawing 4 cards from an ordinary deck and replacing each card after it is drawn. You win if at least one ace is drawn. Again, we're going to go through and we're going to set up our event. And that is at least one ace. That means our complement is no aces. Again, it's easy to find no aces. So the probability of A of C, that means what's the probability of getting not an ace? So this is probably, that is the probability of not an ace. Well, the probability of not an ace is 48 out of 52. And then we're going to do that 4 times. So if I want to find the probability of at least one ace, I do 1 minus 48 divided by 52 to the 4th power, because I need to get that not an ace 4 times. So a hand with at least one ace shows up about 27% of the time. So this is a winning hand. All right. Last one, compute the probability of at least 1 out of 1,000 24-year-olds will die. So again, the event we're looking at is at least one of them dies, which means the probability of A is equal to 1 minus the probability of the complement. In this case, we're looking for that to the 1,000th power, because the complement is no one dies. So this means the probability that at least one dies is equal to 1 minus 0.9986 to the 1,000th power, and that is going to be equal to 0.7536. So that means if we selected 1,000 males that fit into our population range, if we did that 100 times, so we picked 1,000 people and we got 100 different groups of 1,000 people, we would expect at least one person in 75 of those groups to die, which means 25 of those groups, no one would die. In 75 of those groups, at least one person would. That's how we can use those statistics. All right, that is the end of 5.3.